Hello YouTube and welcome to another video. Today I wanted to talk about mathematical logic because it's a subject that is often not really discussed within high school. So this is aimed at high school people who are interested in mathematics or maybe first year bachelor students. First I want to do some outline. What even is mathematical logic? And to explain that I want to talk about often unspoken thing in mathematics where there's two branches. There's like a main branch, and just like you have in a computer game, for instance, you have something like a beta branch where they try to develop new structures for mathematics. And this beta branch of mathematics, that is kind of the study of logic. But most mathematicians occupy themselves with this main branch that doesn't really question the fundamental assumptions underlying mathematics, but just uses some base assumptions to be able to more easily speak about things. And so logic is sort of mathematics turning itself onto itself and analyzing itself. And because of that, it gets very self-referential and sometimes vague and difficult to follow along. I'm going to try to make this as understandable as possible, but just hang in there if it gets a bit too meta and self-referential. That's part of the field, I think. The first thing that I think you should understand when studying logic is there's these mathematical sentences like 1 + 1 = 2. And as a logician, you want to be able to understand what each of these symbols means. If we can break this down into individual symbols, then we might be more easily able to say something about these statements. And so I'm going to introduce three types of symbols. The first one is terms, the second one is functions, and the third one is relations. And I will just say right now that 1, 1 and 2 are terms, plus is a function, and equals is a relation, but I'm getting ahead of myself. Let me start with explaining what terms are. Terms are all the objects in mathematics. So things like numbers, 1, 18 is a term, pi is a term, but sometimes also sets of numbers. So for instance, if you collect the number 1 and the number 3 in one set, this thing is also a term. So this can already get a bit confusing, if you can imagine. And what the term is always depends on the context. So if you're talking about groups of numbers and you want to say something about a certain group of numbers, then you want a group or a set of numbers to be your term. But if you want to say something about an equation or the cross-section of an equation, maybe you want just a normal number. Sometimes you also have vectors, which can also be terms. That's also a set of numbers, but they are interpreted as an arrow in the two-dimensional plane. You might have seen this. So if you have the two-dimensional plane. In mathematics we also group our numbers. So for instance, you have the natural numbers. This is a term, and it's just the set of all integer numbers, positive integers, so 0, 1, 2, 3, etc. Then you have the integers, which is the natural numbers, but also in the negatives. So these are all terms. This equal sign is not a term. Then you have the quotients and the real numbers. So let me go straight ahead to the real numbers. The real numbers are just any number. So you can imagine them as the whole number line. 0 in the middle, and here is maybe 1, and then here is pi, and it goes on until infinity. These are all terms, and of course the two-dimensional plane we call R2. If we imagine R3, which is three-dimensional space with 3 coordinates, we can imagine a cube inside of R3. And this cube is again just a collection of numbers. It's a very complicated collection, there's infinitely many numbers in there. But this can also be a mathematical term. So terms can really be a lot of things, but they're just the objects. One more example. Sometimes a term is something with structure. For instance, we can have the set of all preserving alterations of a triangle, which we call D3. And it is not the triangle itself, but for instance the mirroring across this axis or a rotation here. Every rotation and mirroring is in there, so it has 6 different elements. And we can label them, but for instance we can call the element that does nothing, we can call E, we can call the first rotation R, and then the second rotation R squared, and then we can call the mirroring tau, and we can call the second mirroring R tau, and the third mirroring R squared tau. And this is a collection of 6 objects, terms. This is something you would often see in something like group theory, and this can also be a term, and we call this term D3. So it doesn't have to be numbers, is my point here. And so in mathematics we generally speak about things that are a lot more abstract than numbers. So this is not only a intro into logic, I guess, but also in just the generalizable way to apply mathematics. And so what I want you to have as a takeaway is that what is a term is very much based on the context that you are trying to use something in. In a lot of high school mathematics, terms are just numbers. But in more advanced mathematics, that's often not the case anymore. Okay, next up is functions. Functions grab terms. They can grab 1 term or 2 terms or 3 terms. Let's say you have the function f of x equals x squared. It's a very recognizable function. It grabs a term, in this case a number, and it spits out another term, in this case a number also. So this function grabs the number 2 and it sends it to the number 4, and it grabs the number 3 and it sends it to the number 9. So a function in general grabs one or multiple terms and maps it onto another term. For instance, there's also the function multiplication that we saw earlier, or addition I should say. Addition grabs 2 terms and maps it to another term. So this function we call one-ary, because it grabs 1 term, whereas this function we call two-ary or binary sometimes, but not to be confused with binary counting. It just means it has 2 input terms. I think functions are quite self-explanatory, but the most confusing thing about functions is probably they're kind of unnecessary in a theory of logic, because there's very little difference between functions and terms. Let me explain that. If you imagine our function x squared again, and we map that on the 2-dimensional plane, then we know that this is going to look like this parabola here. And earlier we saw that a term can also be a collection of numbers. So we can call our function a function if we think of terms as numbers, but we can also call it a term if we think of terms as collections in the 2-dimensional plane. Sometimes the line between functions and terms gets blurred a lot, and actually in what I earlier called mainstream mathematics, what I'm really, from the perspective of the logician, mainstream mathematics actually has a name. It's called Zermelo-Fraenkel choice, or ZFC, and later we will see that this is a theory of logic. In the context of logic, mainstream mathematics actually doesn't have any functions. Every function in mainstream mathematics is secretly a term. But the weird thing is that no mainstream mathematician would ever see it this way, because I sound like a goddamn conspiracy theorist. Just to be clear, when I say mainstream mathematics, I don't mean it in a derogatory way. I'm just trying to emphasize that logicians think about these things differently. So in any mainstream mathematical context, a mathematician will think of something like this as a function, but when a logician looks at this, in the context of how a mainstream mathematician uses it, it's used as a term. But we will later see where that nuance lies, and it's not super important that you understand it. Just understand what the function is supposed to do, and understand that the line between functions and terms can be blurred. Now I want to talk a bit more about this distinction between functions and terms, and how a mainstream mathematician and a logician looks at this differently. You have mainstream mathematics, I will call MM, and according to the logician, mainstream mathematics is just the application of what we call Zermelo-Fraenkel choice. So this is from the perspective of the logician, right? The mainstream mathematician does not experience that in this way at all. And this is where logic really comes to an epistemological split, sort of. When you're doing logic, there's two groups of people. Some say it's just like a way to understand mathematics better, and others say that you are really touching on some fundamental cognitive structure of the mind, or sometimes cognitive structure of the universe, depending on how religious you want to be about it. And these schools are kind of denominated by the people working on it. For instance, someone like Russell in his early life really believed that the logical structure reflected something about the cognitive structure of our mind, but later he realized that it was probably wrong, and more common to philosophers is probably Wittgenstein, who had a very similar dynamic over his life. But for the mainstream mathematicians, their guy is really Hilbert. Hilbert was a very practical guy, and he was very good at logic, but he mostly just used it in application on mathematics. So it almost becomes like a theory of what works. If it works, then it is true, right? So in that view, mainstream mathematics has a lot less to do with logic. And this view is called formalism, I would say, but maybe some people will think I completely butcher this. This is the way I understand it. So this is something you have to keep in the back of your mind when you're studying logic. I think studying a bit of logic is very good for your mathematical development, because it elucidates a lot of the way that arguments work and such. But you do have to keep in mind that when people are doing mathematics, that you're not at all really describing their cognitive process when studying logic. And the way that functions are thought of and applied and described by logic is a very good example of this. But to learn that, you first have to learn a bit more. Now I want to get back to this one-ary and two-ary functions. And I want to ask, is there also something like a zero-ary function? So this would be a function that doesn't take any argument and spits out a term. And for instance, the function that always returns 1. And this is just clearly exactly the same as a term, right? But I hope you understand this zero-ary thing. And let me just give an example of a three-ary function. So that would be something like f x, y, z. Let's say 1 minus the square root of x squared plus y squared plus z squared. And you might recognize this as the function that is 0 at the boundary of a ball in 3 dimensions. So that would be a Fourier function. Let me just give that example also. So what you call the kernel of this function is what outlines the ball in 3 dimensions. Let's move on to relations. So relations are really the most important thing in logic. They are what give a logical system its structure. So if functions are the wood, then relations are the tools, if we make a woodworking analogy, for instance. I earlier said that the equal sign is a relation, and we had it in the example of 1 + 1 = 2. So really, what is this equal sign doing? Well, it's eating 2 terms, because we kind of the order is that we first use the 1 + 1, and then there's 2 here and there's 2 there, and it is trying to equivocate them, right? It's asking, are these the same? And it's saying, yes, they are. So this equal sign takes in 2 terms, and it spits out something else. What does it spit out? Well, a truth value. It either says true or false, right? So in this case, it's true. Whether something is true is very important in mathematics. But let's get back to the definition of a relation, and that is, well, this is a two-ary relation. So this comes back here. This means it eats 2 terms, and it spits out a truth value. Now let's look at a one-ary relation. Maybe pause the video, see if you can think of a one-ary relation, and I'll give you 3 seconds to do that. Okay, so my example would be ... is even. This is a one-ary relation. It grabs a number, or it grabs a term. It could also eat a cube, but it will probably say that the cube is not even, because how could a cube be even, right? But let's say it eats the number 2, and then it says true. 2 is an even number. For those who don't know, the even numbers are all the numbers divisible by 2. So 2, 4, 6, etc. And the important part about relations is we could have written down 3 is 2, right? But that is false. In this case, the relation would spit out false. When we are doing mathematics, we have the implicit understanding that every sentence that we write down is true. And that is really how you have to think about mathematics. Mathematics is a tool of communication, right? It's a language where it's impossible to lie, theoretically. So every sentence that you write down has to be the truth. That's the idea. And if it's not the truth, people should be able to tell without your help, without you being able to deceive them. And so relations, they are what gives this truth. I don't have an example of a three-ary relation by hand. They're basically never used. But let's look at the zero-ary relation, because this one gets interesting. It doesn't take any terms, and it's either true or false. So there's only 2 zero-ary relations. And we call these T for true and upside down T for false. Sometimes you will come across a person who's a bit pretentious, and they will say that the upside T is called falsum, which is Latin for false, I think. Well, you can call these relations. Some people don't call them relations, but I think it doesn't matter how you define them, right? If you call them zero-ary relations, that's fine. They don't take in any terms, and they spit out true or false. For those who are interested, there's only one relation in ZFC, or main branch mathematics. It's a two-ary relation, and it is this little included in. And on the left hand side you have a set, which could be the number 2, and on the right hand side you have something like the natural numbers, for instance. So also a set, but a larger set. Well, this is only true if the left side is included in the set on the right, which means the right one is also larger. And this is the only true relation in this theory, but you can define other relations. So what do I mean with that? This one is axiomatically true, whereas other relations are technically definitions. For instance, the subset of. So for instance, 2 is a subset of the natural numbers, just like 2, 3 is also a subset of the natural numbers. So these brackets mean that this is a set containing the number 2. That's not the same as just the number 2 bare bones. But that will come in a later video when we'll talk about more in depth about sets. So time for a little recap. The 3 most important symbols in mathematics are terms, which are your basic objects, functions, which map terms to different terms, but sometimes it's a bit blurry what is a term and what is a function. And I just want to give one more small example of that, and that is functional analysis, or quantum mechanics uses this a lot. For instance, in quantum mechanics you often say that you have a function, like the wave function phi, and that is included in some kind of what we call a Hilbert space, H for Hilbert space. And in this case, phi is a function that takes in spatial components, time components, whatever, and H is a space of functions. So in this case, our function has become the term. So in practice, these two get mixed up all the time. I'm not just making up shit here. And then our last thing was relations, which actually take up terms and they spit out true values, and they are what give the structure to our theories. And they can be things like equal sign, is included in, or is an element of. What other relations are there? Is even. These are the most important 3 types of symbols that we have in mathematics. There's only 2 more types of symbols left. Oh yeah, I forgot the falsum and the true value. There's only 2 more left that are less important for now, I think. Logical connectives. Sometimes actually logic courses start with these, because you can really do a lot of mathematics with them without having to know anything about how to apply this to actual math, which makes it an easy exercise course. But the problem with these is that they are hard to apply to mathematics if you haven't heard these first 3 yet. So that's why I leave them for later. The next one is quantors, and these are maybe the most interesting. So let me quickly go over these 2. Logical connectives take up 1 or 2 true values and they spit out another true value. So there's 16 of them in total, but we only write down a few. A very important one is negation. Not true is the exact same as false. Another important one is this double arrow that I just used. This is only true if the right and the left have the same true value. So true double arrow true is true, and false double arrow false is true. But true double arrow false is false, and false double arrow true is true. Then you have and or, and now you see this part becomes hard to explain because it's become so self-referential with the language that we use, because, well, you get it. These are the symbols for and or, and you can guess what they do with true values. True and true is true, but any other is false. False or false is false, and any other is true. These are both two-ary. This one is two-ary. The negation is one-ary. It just takes in one thing. So here I should have used brackets. Quantors I will get into later. There's 2 of them. There is this one, which means for all, and then there is this one, which means there exist. So usually you write something like for all x in the real numbers, it holds that x squared is larger than or equal to the number 0. This could be a statement. And what this is communicating is that squares can't be negative in the real numbers, for instance. There exists, you can think about how to use that. With these 5, I think we have every symbol that you can use in mathematics except for one. And that one I will write down on another row because it's less discussed and it's really not important. And that is dialect, I will call it dialects. I don't know how to call this one because it's never discussed. So I've never seen it in a book discussed. But it's just, what I mean by that is if you say f of x is equal to x squared, then you have these brackets here, right? These are also symbols that we use in mathematics. The way that logicians get around this is they have a canonical ordering. And how that works is very weird if you've never seen it. But I will just quickly use my example of 1 plus 1 equals 2 again. The canonical ordering for this, I don't know even if that's the term, the unambiguous ordering would be equals plus 1, 1, 2. And then this is called a string. And the funny thing about logic is eventually you can start doing mathematical analysis on these strings. That's really where it gets interesting, but also maybe too difficult for me. Anyway, this is the unambiguous ordering. What this says is you have a two-ary relation, the equal sign. That means it's expecting two, you read it left to right, it's expecting two terms. Then it checks the next box, it says plus. This is a two-ary function that also expects 2 terms. Then the plus eats this one and that one. Those are both terms, so it's happy. And then this says plus 1 and 1. And then the equal sign eats that as the first term, and then it looks for the second term, it finds the 2. And because this ordering is defined and is unambiguous, if you go through it with if you know the aryness of every sign, then it's unambiguous. In this way, you only need these brackets and these commas, but no self-respecting mathematician would ever write an actual sentence like this. They would always just write in their mathematical dialect, which in our case says if you have a plus sign, functions go before relations, so we do the function first, generally. But if you really need to be clear, we often use brackets to denote that something has to be done before something else is done. That one is really not so important. So with these 6 categories, we basically defined every symbol that you can find in a mathematical text. So let me give one more example of mathematical reasoning where I explain what everything does. So I won't use quantors yet, but I will use some logical connectives. If we write down x squared plus 2 is 0, implies, this is a logical connective that I haven't talked about, but it's also very important, the implication arrow. The implication arrow, its truth table seems a bit weird, but you intuitively know how to use it. Every line skip in a mathematical text is also an implication arrow. By assumption, that's a dialect thing. And you have used that on math exams, definitely. But it just means that if the first thing holds up, then the second thing also holds up. So true implies true is true. Strangely, false implies true is also true. But don't think about it too hard, because it will break your brain until you get more used to this. Okay, so we have a sentence here. And logical connectives go after relations. So that's also a dialect thing. So this thing goes, then the logical connective, and then the next thing. Okay, so here we have to use a bracket if we want to be unambiguous. And then we write down x equals the square root of 2. Oh, sorry, I times the square root of 2, huh? X is an imaginary number. Wait, let me change this around because I don't want to confuse people who don't know imaginary numbers. We make it minus. X is the square root of 2, or x equals minus the square root of 2. So this is a full statement, and it is true. and we use two logical connectives here and here. We use, x here is a variable. We split up terms in variables, variable, and constants. So a variable is undetermined, whereas a constant is determined. So 2 is a constant, x is a variable. Yeah, and I said it correctly. It is like this, I think. But the distinction is not so important, trust me. Variables we will talk about more when we talk about quantors. Anyway, x is a term, it's a variable. Minus is a function. It is a two-ary function. Oh, square is also a function, by the way. It's a one-ary function. So we have this function, we have the term, we have the minus, we have a constant, we have a relation, we have another constant term, and then we have a logical connective, then we have a little dialect thingy to get the ordering correctly, because this is also a logical connective, so it's ambiguous whether this one goes first or that one. Then we have the same variable as we used here, and then we have an equal sign, which is a relation, a two-ary relation. We have a square, which is also a function, and etc. You get it. What is this minus here, actually? This minus is also a dialect thing, I think. Minus the square root of 2. You can view this again. Here it again becomes vague whether square root is a function or a term. Because you can say, oh, square root of 2 is just a number, and this is its name. It's a number in the real line, and its name is the square root of 2. But you can also say, no, the square root is a function. It goes from the positive reals to the reals. And, you know, it does what the square root does. It looks like this, like a sideways parabola. And then 2 is a term. So these two are both correct interpretations of the square root of 2, but in one of them it's interpreted as a term, and in the other it's a function with a term inside of it. Anyway, let's check comprehension. I'm going to put a few exercises on the screen, and you can take some time to solve them. Okay, pause the video now for more time. And try to grab some pen and paper, try to answer these two questions. So write down the type of symbols, what sort of symbol it is, and the arity. And if it's a variable, if it's a term, write down if it's variable or constant. And I will give you the answers when my hand is done counting. Okay. So the answers are as follows. I don't know if this is readable, but I will read it out loud. So n and k are variable terms. Plus is a two-ary function. Dot 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 is even is a one-ary relation. If and only if. This symbol means if and only if. This is and, this is or, this is negation. These are logical connectives. Upside down A and backwards E are quantors. Included and smaller than are relations. X and N are variable terms. R and N are constant terms. And let me just quickly, that was the end of the lesson, but I want to quickly say what these two sentences mean, because that's important in learning how to write or read mathematics. Probably I'm using sentences that mean something, of course. Here it really should have a quantor, because this is only true if n and k are natural numbers. This sentence should actually start with for all n, k in the natural numbers, or the integers if negative numbers can be even also. So what is this saying? Well, it's saying if you sum two integers together, they are only even if both of them are even or if neither of them are even. Right? That makes sense. 3 plus 6 is of course odd plus even, and it's going to be odd 9, right? You can think about it. You can try to prove it. We're not going into proofs yet, so I won't go into that too much. But this is a sentence that is true, and you can see how this ands and or and ors are used in a normal mathematical sentence. And this if and only if is very important. It means that it also can go the other way around. If n is even and k is even, then k plus n is also going to be even. Okay, of course 3 plus 5 is, one more example is 8 is even. And 2 plus 4 is of course going to be 6, which is also even. You get it. Next sentence has quantors in it. This one means for every number in the number line. So if we imagine the number line, which we call r, this is the number 0. This is the number line r. Any number that you can pick. Let's pick this number over here. There always exists a natural number n, which is going to be bigger than our chosen number. So this is our chosen number x, and there will always be some. The natural numbers are of course only once in a while you come across one, and for every x there exists a natural number which is going to be larger than this x. That's what this sentence says. This is how you would write it down in mathematical language, and now you know what each of these symbols kind of represent. So if you've never seen this r or this n or this included in sign, I hope you now understand better how they are used. And this was my first lesson of logic. I really hope you enjoyed it, and I will make some more videos hopefully. I found that logic was really under-explained on mathematical YouTube so far. There's a lot of like what I call main branch mathematics on YouTube, but logic I found really not a lot of good sources, so I hope this at least can kind of put a damper on that. But yeah, really let me know in the comments what you would like to see next. And my next video will most likely be on quantors and set theory maybe. We can go into all the juicy stuff. Anyway, that was it. Bye!